So in the last couple of videos, we began looking at the topic of antidifferentiation, and we found that antidifferentiation is essentially the opposite of differentiation. So we're asking ourselves, what is this the derivative of? And that helps us find the antiderivative. And we're going to use this idea to help us find out what the antiderivatives of sine and cosine are. So I want to start off by reminding ourselves what the derivatives of sine and cosine are. And so we can say that the derivative d over dx of sine of x, we know that that is equal to the cosine of x. And likewise, the derivative d over dx of cosine of x, we know that that is equal to the minus sine of x. And what I'm going to do is I'm going to use these two derivatives here, these two known derivatives, to form a little circle. And that circle will make some more sense in a sec. So we'll start off at the top of our circle, and we're going to start off with the function sine of x. And then this red arrow, we're going to come around here, and that means we are taking the derivative of sine of x. And if we take the derivative of sine of x, we end up with cosine of x. So that's saying taking the derivative of sine of x, we get the cosine of x. And well, we're going to do the same thing to cosine of x. We're going to take the derivative of cosine of x. And that leaves us with minus sine of x. So that's just reading those formulas up the top there, straight off the page. Well then, taking the derivative of minus sine of x, so taking the derivative of minus sine of x, we end up with minus cosine of x. And the final one, taking the derivative of minus cosine of x, well, we get minus sine of x. And those two negatives make a positive, we end up with just sine of x up there. And we do a full circle. So when you take any one of these four terms, so sine of x, cosine of x, minus sine of x, or minus cosine of x, and you take their first, second, third, and fourth derivatives, you end up back where you started. And this is going to help us understand what the antiderivatives of all of these are. So as we said, just going back to what we said about antidifferentiation, we're asking ourselves, well, what is this the derivative of? So for example, we are asked to find the antiderivative of sine of x with respect to the variable x. Well, what is sine of x the derivative of? Well, looking at sine of x is the derivative of minus cosine of x. We go the other way around our circle. Because minus cosine of x, if we take the derivative of that in our red arrows, we get to sine of x. So we can see there that the antiderivative of sine of x is equal to minus cosine of x. And we have to add our c on the end. We always remember to plus c with antidifferentiation. And likewise, we can do the same with the antiderivative of cosine of x. So the antiderivative of cosine of x with respect to the variable x, we find our cosine of x, and again, we go against the red arrows. We go the other way. We're going anti-clockwise. And we see there that what is cosine of x the derivative of? It's the derivative of sine of x. And we always plus our c. So that's essentially our antiderivatives. And I just want to come up with a proper formula that we can use. Okay, so you see what I mean in a sec. Firstly, I just want to revisit the official derivative formulas that we came up with a few videos back. We said that the derivative of sine of some function of x, this can be any function of x in here. Okay, so that could be x cubed, it could be x to the power of 4, it could be x squared plus 6, it can be any function of x. The answer to that, the derivative of sine of some function of x, well, we take the derivative of that function of x and we multiply it by the cosine of the original function in there. The bit in the middle never changes, and you'll see that's the same with antidifferentiation. This part in the middle here, in those brackets, it never changes. And we can do the same for the cosine of x. So if we do d over dx of cosine of some function of x, this gives us negative the derivative of that function of x multiplied by sine of the original function of x. Again, that bit in the middle, it's never changing, that f of x there. All we're doing is we're multiplying by the derivative of that. Okay, well, that says that f of x can be anything. Okay, f of x can be any, it can be any function of x. That's no problem. But when we come up with our antiderivative formulas, and I just want to keep that bit in purple there, we're saying that the antiderivative of sine, and in this case, we can't just put any function of x. Our formula only works if that function is a linear function. So it has the form for a linear function, ax take b. Okay? So it has to be a linear function, because if you put into your calculator, what's the antiderivative of, say, sine of x squared, your calculator would struggle. It won't give you an answer. Okay, so the antiderivative of sine, and it has to be a linear function in there with respect to the variable x. We come up with the formula, we get minus 1 over the derivative of what's inside. Okay, well, the derivative of what's inside there, that's going to always be our a. The gradient or the derivative of a linear function is always that a term. So we get minus 1 over a times the cosine, and the bit inside never changes, even with antidifferentiation. We get ax take b. And we always put plus c on the end there. And we can expand this idea straight into the cosine of x as well. So the antiderivative of cosine, and again, it has to be a linear function in here, okay? Dx is equal to 1 over a times the sine of ax take b. The bit in the middle never changes. And all we're doing is we're multiplying by 1 over or minus 1 over the derivative of what's inside here, the derivative of this ax take b. And that will always be our a term. And what's important to note here on both of these is such that a is not equal to 0. Okay, and there's a couple of reasons for that. If a is equal to 0, then here we would be dividing by a 0, and here we would be dividing by a 0, and that's not allowed. But if we are finding the antiderivative of cosine and our a is equal to 0, so we're just left with our minus b, we're just left with a constant there, for example, 2. Well, this cosine of 2, what does that become? Well, that's just a constant. That just gives us a number. So all we're going to get for our antiderivative is multiplying our constant by x. We're adding 1 to the power of x, and we're dividing by the new power. So we get x to the power of 1, so we get x times the cosine of 2, divide by the new power of 1. We just get x times the cosine of 2. So that's just a little tangent that we've gone on there to explain that it's important for two reasons that a cannot be equal to 0. Okay, well, we'll erase this, and we will come up with a couple of examples using these very important formulas. And these formulas here are the ones that you'll most likely see on your formula sheet. Okay, so we'll highlight those in yellow. They're very important. And the most important part to take from this is that they're very similar to our derivatives in as much that the derivative and antiderivative of sine and cosine are sine and cosine respectively, and they're all intertwined. But we have to make sure that here in our derivatives we're allowed to have any function of x. Here we're only allowed linear functions of x. Okay, well, let's do an example. Let's say that we're asked to find the antiderivative of sine of, let's say, 3x plus 2 with respect to the variable x. Okay, well, from our formula, we see that this is a antiderivative of a sine function. So we're going to use this formula on the top here. So we see that 3x plus 2, in this case, has to be equal to our ax take b. And we see in this case then that a is equal to 3 and b is equal to minus 2. And what we do is we put that straight into our formula, and we just put those values in. So we get minus 1 over a, or the gradient or the derivative of what's inside. So minus 1 over 3. 1 over a is equal to 3. And then we multiply that by the cosine of ax take b. That bit in the middle then never changes. So we end up with times the cosine of 3x plus 2, and we always add c on the end. And that's just a little example there for the antiderivative of sine of 3x plus 2. All we're doing is we are finding out our values for a and b. A is equal to 3, b is equal to minus 2, and putting them into our formula. In other words, we're doing this minus 1 over the gradient of what's inside. If we take the derivative of 3x plus 2, we just get 3. So we're doing minus 1 over the gradient function, minus 1 over 3, times the cosine of exactly the same thing. That never changes. And we always plus our c. Well, that's pretty much it for the antiderivatives of sine and cosine. All you really need is just these formulas here and be able to just substitute in some values. But it's good to see sort of where it comes from. And it all comes back to this little circle here, and back to the idea that the antiderivative is just asking ourselves what something is the derivative of. We're just going the other way around that circle there, anti-clockwise for antidifferentiation rather than clockwise for differentiation. Okay, thank you.